is basically if we have a contact angle, so a plate moving relative to a fluid, how does the contact angle, when it starts moving, going to depend on the speed of the plate? Okay? So this is instead of just the equilibrium contact angle, if it moves very slowly, as you see here, the equilibrium contact angle can be maintained, but if the speed increases, then the contact angle will change. And we'd like to be able to understand how that works, and that's, of course, going to then determine the force resisting the motion of a rolling drop. Okay? And the other issue we're going to look at is spreading. So these are basically both spreading. So if we put a drop of surfactant or a drop of oil on a surface of water, how quickly is it going to spread? And this is, of course, important in the context of oil spills. So here we just sprinkle dust on the surface of water, then we release a little drop of oil or surfactant, and it spreads outwards. So what's R as a function of T, right?
So that was first dust, and then there was a drop of surfactant?
Yeah. So in all of these things, and this is sort of one of a general class of problems which I'll treat, which is gravity currents. So gravity currents, basically things spreading under the influence of gravity. These things are not spreading under the influence of gravity. They're spreading under the influence of surface tension. But we want all of these different, so lava flows. When in the morning, if you make pancakes, you put down and it spreads. How do we describe the radius as a function of time? So for this entire class of problems. Okay, so the first one is this contact line problem. So actually we won't need this anymore today. Okay, so today's lecture is on spreading. So the first issue is what happens if we have a contact line and it wants to move. How quickly can it move? What force resists its motion? Okay, so the basic physical picture is what we saw in the video. Oh, by the way, are there any questions on the problem set? I think you guys should be able to solve them all now, right? After class or before? Okay, yeah, after. Yeah, after. Okay, very good. When you're not being filmed. I'll agree with that, yeah. Okay, so we have if we're static, then we know that this thing comes in at the equilibrium angle. And then if it's moving slow, so this boundary now is moving, then you're going to have some contact angle theta d, which is less than theta e. Let's call it. So this is a dynamic contact angle. And if you go faster, then the contact line doesn't have time to move, and it basically gets stuck, and you place a film on the surface. So we mentioned last time some applications of this. This is an important industrial process. So let's call this a plate. So velocity of the plate. If the velocity of the plate increases fast enough, you'll eventually place fluid on the solid. So we talked about fiber coating as an application. Also, you can think of this as in the oil industry, when you're trying to get oil out of porous rock, you're pushing water in. And so if this is then the water, this is the oil. If you're leaving oil behind, it's a bad thing, right? So you can ask, how am I going to optimize the system? How am I going to get the most fluid out with the most oil out with the least work? Okay, so these, and on this scale of porous rock, capillary effects are very important. Okay, so the other, if we imagine a tube, so we have vapor phase, liquid phase. We have a static value here, and then if we start driving the interface, as here we'll get a situation where we get a contact angle theta d, which is less than theta e. And at higher speeds, you'll leave a film behind. Yeah. That's right. That's right. Yeah. In the video, we were pushing down, and so this thing was coming down. Yep. Oh, yeah. Yeah, it's cool here. Try it over here. Well, yeah, if you move it slowly enough, right? So this is what we want to figure out. Yeah. Okay, and so what one observes is the following, and this is what we want to rationalize, the shape of this curve. So if we look at the theta, so what is the dynamic contact angle as a function of plate speed? So there's a maximum speed beyond which you get a film, and we know that we're going to start with theta e, so when v is equal to 0, the contact angle is just the equilibrium value, and then things look like this. So this is empirical fact. And so this is where we start. How do we rationalize this? Well, we see here that theta d okay, so Okay, so if we have a contact line advancing, so let's say the equilibrium value was this. If this is a fluid front, just imagine that you have a drop advancing, then the dynamic angle is going to be greater. So that's the force moving the drop, say. So this is this advancing drop, liquid vapor. So if we have now a retreating drop, okay, so this thing's now moving in this direction. Okay, so what's the force of traction pulling the contact line? We know that theta E represents the equilibrium value, so if it's at theta E, then there's an equilibrium at the contact angle. But because theta D is other than theta E, there's a net force acting on the contact line. All right? Okay, so note. Okay, so what we're going to know is how does this force depend on V? And so how do we rationalize this?
John, quick question.
Mm-hmm. Mm-hmm.
Maybe I'm missing, because that pattern doesn't quite match this force meter pattern, right? I mean, over there, the D is in the front, theta D, and so on to the angles. We're rationalizing that.
It should be the same. You're saying this one's different from this one?
No, this one's different from the one you wrote there on the right.
So here you have a vapor advancing into a liquid, right? So this is a case where
This is vapor. I can say
this is
vapor,
vapor, yeah.
into a liquid.
Yeah. So
And the other one's liquid into vapor.
yeah.
Oh, that's what I'm saying.
Okay. Okay, so this is again this sort of case when you're extracting. This is sort of extraction. Think of. So you're basically pulling a plate out of a fluid, and here you're pushing air into a fluid. Okay? So this one, So this corresponds to so it's just a question of whether the contact angle is moving forward or backwards, right? Okay, so there was a series of experiments done on the advancing case by Hoffman for the case of a wetting fluid. Okay, so here you imagine you have a piston, so it's the same sort of geometry as we have up there. We're pushing fluid, a wetting fluid, into a tube. So at a speed v. So we have our liquid. It's a wetting liquid, so the equilibrium contact angle is 0. And we're interested in how theta d changes with speed. Okay? Okay, so the observations. So we can plot this in terms of a non-dimensional parameter, that being the capillary number. So these are just fluid properties. So this is basically theta d versus speed, and it looks like this. So you start off at theta e equals 0 when speed is 0, and then it goes up 280, 90. Looks something like that. So it's saying that you go fast enough and eventually you wind up, this reverses sense, the meniscus. Right? Okay, and so if you plot that on a log-log plot, you get a famous relation which has been lurking around for a long time and has only recently been rationalized. It's something called Tanner's law. So So it basically looks like so we get a log-log plot, and we get a nice scaling relation coming out, and the slope of this is 1/3, which tells us that theta d is going as capillary number to the 1/3, and so as the speed to the 1/3. Okay, and so rationalizing this, is our goal for the first half of the lecture. And there's one slightly dodgy part. This is due to de Gennes. So if you're going to do something dodgy, as long as you cite someone who has a Nobel Prize, you're fine. So, and I'll let you guys spot the dodgy part. It seems perfectly reasonable and it works, but I would not dare to publish it. Okay, but I tell you, these French and their scaling arguments. What's that? Even de Gennes, yeah. No, but it actually touches on, this is a very interesting question. And it was this is one of these taboo subjects when I was a grad student, like moving contact lines. It's one of these situations where mathematicians get very excited because there's a singularity, right, in the equations. But I mean, on the other hand, it's not surprising that the equations break down because you have the continuum hypothesis, which we know is true up to, down to a scale of about 10 molecules. And then the contact line is literally a point, right? So things are going to break down there. So, of course, singularities appear in the equations, and everyone gets all up in arms and start talking like there's a black hole in the middle of the universe, when it's just, you have some approximation which is going to break down at the contact line, right? Yeah. And people feel very strongly about this, so they do about turbulence. So this is the two taboo subjects when I was a grad student. Turbulence and contact lines. So don't go near those ones. But de Gennes has a very nice patch on this problem, as we'll see, and I think more or less solve it. So the question is how do we describe the motion of a contact line? Basically, what's actually happening locally? Where's the dissipation coming from? And how can we characterize it in a rational way without violating the continuum hypothesis? So it's actually kind of a hard question, right?
Because the point of contact indeed is the one that really has a big impact on the dynamics.
Yeah. And as it's getting smaller and smaller, you're saying, well, what's actually happening there? You're getting gradients on an infinitesimally small scale, if you like, right?
It's almost like a good situation for like a multi-physics model.
Yeah.
Right? Two models, one local, right?
Yeah, because they do molecular simulations, and that's the sort of thing that would be, it's going to be particularly useful there, right? Because you can actually get at the local dynamics. Right, because if you say, what's the local stress at the contact line? Well, if you zoom in close enough, you're getting gradients over over an infinitesimally small length, so things are going to blow up. But okay, so that's the sort of background. Is this moving contact line was a really hot topic, and a lot of people had tried and failed. But there's a very simple experiment done by Elizabeth Dusan. I read this and I couldn't quite see what the whole problem was. So again, it's like, how does a contact line actually move? I mean, okay, so let's put it this way. We have a drop, and it's got to advance, right? But there's a no-slip condition, right?
Yeah, that's a big
Right, so you have no slip. So how does the thing move? Well, I hear people make that argument. I go, that's a rubbish argument for the following reason. And so ready? So what she did is these are really nice experiments. She looked at drop motion, so exactly this problem. Drop wants to move in this direction, and she put a blob of dye on the surface. Okay? Step it forward, and you see that the blob of dye gets swept down, right, as it advances. Eventually the blob of dye gets there, and then there, and so you see that the thing advances through a tractor tread, like a tractor tread. It's basically going like this, right? So you're not violating the no-slip condition there. The fluid is rolling past it, right?
So it's not the same point in contact.
Yeah, exactly. Right, exactly. So the thing is, again, it says rolling over the contact line. You see the distinction?
It's almost like you push this thing to roll over, and then it very quickly adjusts to if you stop to its equilibrium angle, so it looks like nothing changed.
That's right. exactly.
So
Yeah.
the tractor thing is a good idea.
Yeah, yeah. I think it's a very nice. It makes clear. It gets around this whole business. Oh, there's a singularity at the contact line. Well, I mean, right? So, okay. So if you look at the contact line. Okay, so then the flow near the contact line, so it's locally a shear flow, right? Because the basically fluid is being, well, let's zoom in here. Flow is basically doing this. It's stuck there and advancing like that, right? No? So let's consider the case.
And basically, the tail of the tractor tread is basically lift by angular momentum. That are you think that lifting?
Yeah, that is that's a trickier one.
That's a tricky one.
Yeah.
Lift.
Yeah. That is a good one. So, okay, so, but locally we have, so if this is our dynamic angle, we have a flow which looks like this. So you basically have a local shear flow near the corner, okay? So although it doesn't, it just looks like the thing's sliding along like this, there's actually local shear in placing fluid. Okay, so let's consider, and now I'm going to show you the dodgy trick. Okay, so if we consider the case where this angle is small, then we can write the slope. Is approximately the angle, so we can write z equals theta dx. Okay. So then the velocity gradient velocity gradient like that. And so what we want to do is calculate the viscous dissipation in the vicinity of the contact line. And I don't know if we've done this in this class, but you should know this in fluid dynamics. You can always calculate the dissipation within a flow if you know the velocity field. So this is v. This is the velocity here, and so this is the rate of dissipation. So generally, dissipation within a fluid is mu grad u grad u. Okay. Okay, so, right? Does that look familiar? So you basically do that. So you basically calculate all the velocity gradients. This is the stress, the deviatoric component of the stress tensor, and you dot it with itself, and you integrate over the volume. And that gives you the rate of dissipation within a fluid. Okay? I think it's 2 here, actually. So the largest velocity gradients in this problem are basically dv dz, so we can evaluate this. So for example, if you want, I give this to my class, my first year class in fluid dynamics. I say calculate how long it will take you to warm your bathtub up by stirring, right? Because you can make an estimate for the velocity gradient you get by paddling your hand, and you know what this is, and so you can calculate that it'll take you the rest of your life. But it's just a good thing to have a handle on, right? But it's basically how is mechanical work transferred into energy, right? So this rate of dissipation will then go into heat ultimately, right?
Very smart way of read.
Okay, so we're now going to evaluate this rate of dissipation in the corner. So we have to define what the corner is to begin with, but we have a sense that the smaller the corner, the higher the rate of dissipation, because again, we're getting sort of we're getting around this problem of there being a singularity here by assuming that there's linear shear, but we then have to put bounds on the corner. So we have to define the regions of the corner, and this is what the trick that de Gennes did. Okay, so this we can say, so this is, say, per unit length into the board. Imagine we have a two-dimensional corner. Oh, no. Sorry.
It's like a ramp, right?
Yeah. And so then dv dz we just we've evaluated here. So z is going from 0 to theta dx. Sorry, my nomenclature is unfortunate here. V is the velocity, right? As this is volume. So let's keep that. Okay, so and here comes the dodgy bit. Okay, so we get an integral, which we haven't done anything. There's been no sleight of hand yet. We basically assumed that there's a linear shear flow in the corner. And now we have to say, well, what are our bounds on x, right? So again, this is basically x here. And this is z. What's that? So basically that's all, we're saying that we're integrating over the entire corner. We have to define what the corner region is, right? So we're assuming that there's this region in which you have a shear flow, right? So in fact, you want to go from 0 to infinity. You want to say the whole thing, but we want to cut it off at some stage. It's part of the problem. And so, as I said, I don't know whether he had his Nobel Prize when he when he did this, or whether he won the Nobel Prize because of it. But here's what de Gennes said. So we basically have this guy. And so he's going to cut it off. We're going to get in trouble if we evaluate this at 0. So we're going to put a cutoff on the upper and the lower, and it's fair enough to say that this is cut off on a molecular side, on the molecular scale, right? You say A is the size of a molecule, right? So this is
10 molecules, no?
so yeah.
Is it on the side of a molecule or the continuum mechanics approximation?
He said a molecule, but I think because you have a logarithm here, it kind of the factors. As long as you don't get an infinity, the factors, a factor of 10 inside a logarithm isn't going to kill you, right? So then he said this is the drop size. Okay, so if you do that, then you get this is equal to ln of L over A. Okay. Okay, and so this we'll define as L sub degen. And so this seems to work. This coefficient that we get, this fudge factor, which we make, again, we're making the argument this shear region is limited in extent. We can basically cut it off on a molecular scale and on the lower bound and cut it, but then integrate over the entire drop. I think it's because of this logarithmic dependence that this works. So the experiments suggest that LD is between 15 and 20. Okay, so maybe he just got lucky. Maybe he has much better physical insight than I do, which is entirely possible. But that's the argument, right? Entirely possible / probable. Okay. Okay, so if we look at the energetics now, we can say FV is equal to 3 mu LD over theta D times V squared. So this is the rate of work of surface forces and this is the rate of dissipation in the contact line, right? Because so this is, yeah?
Sorry. And when you say the experiments tell me that the L Lejeune goes from 15 to 20,
Yeah.
it means from like playing with different types of bubbles and so on?
Yeah. Yeah. Different drops.
Which means if L increases, A also increases? To keep this thing balanced?
It suggests, so basically this gives a fudge factor, right? So we have this fudge factor now floating around in our equation, which is this. And but then when you compare to all experiments, it seems to be entirely robust, and this fudge factor has a limited range, so between 15 and 20.
This limited range means if a bubble is L longer,
Right.
then it's like the tip is smoother, and it's bigger,
Right.
right?
Yeah. So that does have this in it. So true.
So it's like a bigger bubble, sort of a round. The tip is not so sharp.
Yeah, I suppose that's right.
Like
Yeah,
it's more
yeah, because this does have a geometric dependence on the drop size. True. Yeah, yeah. This is typically true for the interested particularly in smallish drops here, so we don't have to worry about gravity and so forth. But in any case, so another classic fluid mechanics argument: you say the rate of work done is equal to the rate of dissipation. So when you calculate, say, the rise of a bubble, you say you can do it by calculating the rate of work due to buoyancy, which is so it's going to be the buoyant force times the velocity of the bubble, and then you calculate the total dissipation within the fluid. Okay? So if we do this, we substitute in our force. So again, our goal is this guy, Tanner's law, right? Okay, so in the limit of these things being very small, sorry. Then we know that the cosine of these angles so we can write the force okay, that's so then we can sub into here. Okay, so we get the contact line speed now. Okay, so let's define it in terms of the capillary speeds. So we have our fudge factor. So our V star here is gamma over mu. Okay, so it's just definition. Okay, so notice that this gives us Tanner's law when theta e goes to 0. Okay? So again, you can dislike this argument for many reasons, right? But one develops theory to rationalize data, and we have this data set, right? So this does provide rationale for Tanner's law. Okay? And I would suspect that if you worked from first principles and didn't have any data and tried to develop a theoretical model for a contact line, you would get something which made no sense at all. And then if you did compare it to data, it would be wrong. So this is a theory constructed specifically with a view to rationalizing data, and it seems to do a pretty good job. So I think, again, the most important thing in any modeling, so this is very basic modeling, really scaling arguments, but you want to try and extract as much physics as you can out of the solution and see if it makes sense. So here we see, first off, this rationalizes Hoffman's data. Which is obtained again for the case of pure wetting. So the speed goes as dynamic contact angle to the third power. Second thing we see, of course, V equals 0 for theta D equals theta E. Okay, and you also see that the velocity goes to 0 as the dynamic contact angle goes to 0, because you're then getting huge dissipation in the contact line. What's that?
Over there up in the corner, you wrote cosine of theta E over D.
Yeah. So you're assuming the angles are both small.
So you say it's either one is approximately that.
No, either one, yeah. E/D, yeah. Okay, and we can also see that this speed has a maximum, right? So V of theta D Okay, so when theta D is equal to theta E over square root of 3. Okay, and you can then evaluate the associated maximum speed. And then we can go back and see how this compares to the very first plot we showed of theta D versus V. Okay, and so this is, we come back to our original plot, you can see we can now rationalize its form. Theta, okay, this is theta equilibrium, theta D, and this is theta E over square root of 3. So above here, so if we go, so we have this maximum speed beyond which it turns out that the film is deposited. Okay, and this is a source of continuing debate. So we're really on the front lines here in terms of moving contact lines. This is the state of the art. This has been done fairly recently. And debates as to what's going on here continue, but this provides at least rationale for this curve. Okay?
So you have also a linear term of theta D, right? 'Cause
Yeah.
it doesn't make much of a difference?
No, I mean,
For big angles, probably it doesn't, right? But
yeah.
for small angles,
In any case, you can plot it, right? Yeah, so, yeah. But in any case, you can connect the dots there. Okay, and so, so if we just look, for example, in water, there's a V star, which is our surface tension over mu. It's fairly high. If we choose and our magic number to be 20, then we get a maximum speed of 0.2 millimeters per second. So this is the speed if you pull a plate out of the water, beyond which you'll entrain a film. Okay. Okay, so you can think about that one. And of course, it will depend on the chemistry of the thing you're extracting, but it's not unreasonable, right? If you're pulling a plate, a glass out of water, you can see the emplacement of a film. And if you go too fast, you'll get one. You do have to move it fairly slowly to keep it from fluid from entraining. Okay, let's take a break. We're at the halfway point. Okay, so that's the dodgiest part of the whole course right there. But what can you do? You have data, and this does provide some rationale. I mean, I think this is a nice insight. I think modeling the local.
It's approximating this interval.
Yeah. Yeah.
Desingularizing the interval.
Yeah. That's right. That's right.
But
And with the
surface roughness which generates that hysteresis.
yeah.
Is it or not?
Yeah, so that comes in as well, right? We're kind of looking because this is exactly. We're ignoring the role of surface roughness here. We're basically saying let's imagine it's perfectly clean.
That is why it's generating all the problem of hysteresis.
No, that's true. I mean that comes in as well. Like in reality, there will always be complications at at any moving contact line because there's an additional cost to moving it. But this is saying even if it's moving smoothly like a wedge, there is going to be some resistance to it, right? And this is simply
Due to viscosity or
well, no, because there's viscous dissipation associated with this, right? Yeah. With moving that, and that's what we've calculated. In reality, you have to overcome that plus the corrugation of the interface associated with what? So that's basically contact angle hysteresis. That's the origin of contact angle hysteresis. And so you're also going to be fighting against that. But you do have even if in a clean situation, you have to worry about this. Right?
yeah.
So in an experiment, you're going to get it's going to.
Really no soft surface.
Yeah, exactly. So this is right for a perfectly clean system, which of course never exists. And then again, you have that additional cost associated with the inhomogeneities on the surface, either in texture or in chemistry.
Because there's friction coming from viscosity, which means friction coming from
that's
the chemical.
That's
The chemical aspect of and then there's also friction coming from roughness.
Yeah, that's right. That's right. Yeah, that's an issue. Yeah, that's right. That's right. Yeah.
Yeah, I realized before that the problem with hysteresis was only the roughness.
That's right. That's right.
No, man, it's not only that. You have also the problem of viscosity.
Right. No, that's right. Yeah.
You have a very smooth surface.
No, that's right. Right. Yeah. Yeah.
It's a chemical reaction.
Yeah, because in terms of the interfacial energy, there's no cost to a contact line moving, right? Apart from the change in wetting energies, right? But we're taking that into account here. But there is a here we're calculating the energy loss associated with dissipation, and that's again coming from shear flow near the contact line, right? But then in reality, there's this one as well, right? So we're trying to just separate them.